minute or two. All right. Just give people another minute. All right, well, let's get started. So I'm very excited today to have Anuj Babai, Associate Director in the Advanced Analytics team, provide a talk on decision trees. So Anuj, I'll turn it over to you.
Thank you, Jason. Let me see if I can start share my slide. You can see my slides.
Yep, looks great.
Okay, well, thank you very much, Jason, for introducing me to everyone. And this is my almost like 4 months into my current position. And
so I have been.
Please mute if you're not Anuj, unless you have a question.
I have really loved my experience here in the company and the guidance and the incredible help that I've got from my peers is amazing. I've been working on a project for last few months and with Jason leading the group in that project. And this project is using a decision tree. And so that's the reason today I'm talking about decision tree. And it might be very elementary for some of you actually, and my apologies in advance. So with that, let me also give a little bit of what I will be covering here today. We'll be talking about different methods that people use in economic evaluation. These are common methods and what is the purpose. And then I will go particular method, which is decision tree in economic evaluations. I'll be talking some mathematical concepts that is related to these trees. And working on some precise steps with certain examples. So that would be the rough outline. But before I go, let me, since many of you might not, I have not particularly met with you all. So I want to give some brief outline of my background first, so that you know what I have done in the past. So my undergraduate degree is in physics, chemistry, and maths. Physics and maths was my major, and my minor was chemistry. And then I did, yeah. And then I did my mathematics graduate master's program, followed by from Indian Institute of Technology, Kanpur in India. So I'm originally coming from India. Then I did my PhD in applied mathematics. Let me tell you, when we say applied mathematics, it is still very pure mathematics. So I did work in stochastic processes, which is, there's a dynamical system. And then if you add a stochasticity to it, it becomes a stochastic processes. So my PhD was in applied mathematics, and followed by a couple of postdoctoral fellowship at Cleveland Clinic, Ohio, which was in infectious disease department. But again, I was developing models which were dynamical system based, stochastic processes based. and followed by a second postdoctoral fellowship at Case Western Reserve School of Global Health. And now I am at PRECISIONheor. Every day since the first day of joining, I really not been thankful to the God that I really loved the position. So amazing work and amazing peers. So this is my brief background. I hope, let me go forward. So how is economic evaluation carried out? I mean, so I'm new to this area, so I kind of dig the literature and try to look for what are the methods of it. So there are, well, the whole idea is there are different course of actions, and each course of action has a direct cost and opportunity cost associated with it. And basically the goal here is to compare these alternative course of actions and find out the best possible way. So I think many of the studies are also using incremental cost ratios to compare the effectiveness of the alternative strategies. So that's the idea. There are different methods that are used in economic evaluation. For example, system dynamics models, which are time dependent, space dependent, discrete event simulation, Markov chain models, individual sampling models, and so on and so forth. But this chart is a beautiful chart, which is coming from this study by Barton. Basically helps you guide when to use which method. So for example, what model should I use? It starts with, and it talk about whether there is an interaction between individual or not, whether individual interaction is important or not. So if it is yes, then you do either of discrete event simulation or system dynamic model. But if you say no, then you ask whether recursive event is there or not there. And if it is there, then you go about doing individual sampling model. But if it is not there, then you talk about decision tree. And that is what my focus is today. And also in this thing, if there are lots of health states, then Markov models might be useful in some cases. So this is a beautiful chart which helps us guide where to which method to use. But today I'm only focusing on decision tree, by the way. So, well, usually why do we do economic evaluation in general? Any of these methods, why do we do that? I mean, a few reasons that I have listed down on the left-hand side is trials do have a limitation, such as patient may not be representative of the whole population, for example. Or interventions that you are trying may not be, may be unsuitable for certain populations or certain settings. So in order to do that studies using models, in models you can kill people, you can talk about many things which is maybe ethically not possible or practically, physically not possible in real life experiments. So that's where this, and where the cost is also an issue, then you talk about economic evaluation in general. So what type of data we use in these models? Well, there is randomized controlled trials, there's patient-specific data from social surveys, pharmaceutical companies' reports, published papers and books. So mainly among those set of the documents that you use for estimating parameters for these set of models. So this is general about economic evaluation. But let's talk about decision tree. What is the precise purpose of decision tree models? The criteria for choosing alternative decision, it's the same idea as any economic evaluation method is. A decision tree, we do the same thing. But here you also have chance and probabilities in each decision. It's not always one alternative will occur or not occur. There is always a chance associated with certain possibilities. If you want to know, if you know that early decision is affecting later stage decisions, then also decision tree might be helpful. But again, decision tree is not time dependent model. So it's not dynamic models, although we can build a time in a very simplified way in some sense. Also, when we are interested in quality, if we want to quantify the value of information for some things, then also you use it. As I said before, if you extrapolate to the other population for which the data is only limited, you can do that to assess the heterogeneity in the outcomes. Also, you can do that. So these are the possibilities where you can use decision tree models in that. Graphical, you see everything all together simultaneously, all the alternatives that are there, all the alternatives are the words we use that is strategies, and the probabilities associated with outcomes are there, and what are the consequences in terms of cost, for example, for each alternative or each strategies. All of these things, you see it at once with this graphical tool. And so that's the beauty of it. You are seeing everything in many of these dynamical model, for example, things goes behind the scene. It is not possible to depict each and every component in one picture, for example. Sometimes it is very difficult. So, but in decision tree model, it is very simple to show all these things. Again, the goal is to find an optimal decision among all the alternatives that you have started with. That's the goal. So, but in order to do all these things, you need some basic understanding. Of course, these are very simple ideas. I just wanted to throw this formulas here. Of course, the probability comes from observed frequency from the field studies of certain things that you are talking about. And if there is any experiments done, then frequency count helps in calculating the probabilities. One of the important aspects that we use, although we never say it explicitly, is mutually exclusive events. Basically, mutually exclusive events means two things are happening, but there's nothing common in it. So for example, rolling a die, coming odd versus coming even, they cannot be intersection. If you get odd, you cannot get even. If you get even, you cannot get odd. So these are mutually exclusive event. The figure is showing on the right, top right, basically. Important also is a joint probability distribution. And this is joint probability is basically, think about this as a normal distribution in 2 dimensions. And there is the 2 words we use very often, joint and marginal. So joint is a complete distribution that you are seeing here in this picture, but marginal distribution is a slice of this distribution, just slice like this. Anywhere you vertically slice this distribution, that would be considered as marginal. For that particular x1 value, what is the distribution of x2? Basically, so that's a marginal. But joint probability distribution is what we are interested in many times in this thing. In fact, not distribution itself, but joint probability we are interested in. Probability of A and B, A intersection B, for example. Now, another concept that is also, we use it very often in this decision tree are conditional probability. Conditional probability is same. So suppose we are interested in calculating probability of B. So the difference between probability of B versus probability of B given A is that you are scaling the probability by 1 over probability. So the denominator is different here, but probability of B is on the complete set, on the complete sample space. So, well, if I would have computed probability of B, it would be divided by whole sample space. But if you are computing probability of B given A, then it is, you'd first take an A and then you find the region which is of probability B, set B. So it's little different, little tricky. It's the denominator is different, and that's make it quite interesting. And there's a very good relationship between joint and conditional probability, which is A probability of A intersection B, or A and B is equal to probability of A given B times probability B. This is very standard formulas, but just these things we use very often. So another mathematical concept that we use very often is expected value. Very simple formula, which is saying describe the expected monetary return of an experiment. So these are the possibilities. Xi's are the possibilities, and probabilities are given by capital P. And then a product of each possibility with its corresponding probabilities, and sum it over all the possibility. That is an expected value. So it's basically, so let's see very simple examples, and I will go in simple ways and to go over my main example later on. So which investment is better? Suppose there are two projects, project A and project B. Where should we invest more? If you invest in project A, the past history tells us that you will lose $26,000, and the probability of losing is 0.3. And if you break even, this is 0.5. And if you profit it, it's 68,000 with a probability 0.20. So there are three possibilities in project A. You can lose, you can break even, or you can profit. Same thing in project B. You can lose with certain probability of some amount of money. You can break even with certain probability, and you can profit it with certain probability. If you have two projects like this, which one is better? So expected value is very useful in this regard for examples. And you can calculate it. Suppose this X is is a variable that I'm using for project A, and Y I'm using for project B. Then basically you can write X1, X2, X3 are the three values given to you for the money received from project A, and Y I'm using it for project B. So these are three values for X1, X2, X3 given. Break even means $0 basically, and loss means minus, and profit means positive. Same thing here, minus $0 and positive, and corresponding probability of each one of it is given also in this way. So if I use this expected value formula, it is very simple to find the expected value of X. I'm using the product of each value times the probability, and that will give us the expected value for project A and expected value of project B. So it very clearly says that which project you can see the final expected value that will help you decide which investment is better. So of course, it seems like project B is better for us. Okay, so this is the usefulness, and this is the formula we use in the decision tree, and very often. And I will show you. One of the other components of the decision tree is sensitivity analysis. Anything we do, we are using model estimates from the literature. And when you do from the literature, we are not doing the experiment. Sometimes it's not apples to apples. It is coming from a different study, different experimental designs. So it is advisable to do sensitivity and uncertainty analysis in that. So these words are commonly used in the literature, but there is a minor difference, a subtle difference between sensitivity and uncertainty analysis. So sensitivity analysis is contribution by the inputs. What are the contribution that inputs of the model is making on the final uncertainty of the model? So that's a sensitivity. So contribution of an input is the sensitivity analysis, whereas uncertainty analysis assesses the uncertainty in the model outputs. It's on model output that we are interested in knowing how much is the variation we are observing in the model output. That's an uncertainty analysis. So that's a subtle difference. Sensitivity analysis is on the inputs, and uncertainty analysis is on the outputs, by the way. So there are different methods in sensitivity analysis. You kind of very basic idea is to vary the parameter that you are not unsure of or you have less confidence in. You want to vary it in its confidence interval and want to see how sensitive that parameter is with respect to the other parameters in the models. And there is deterministic and there is a probabilistic one. Probabilistic ones are also called as global sensitivity, where all the parameters that you are uncertain about varied it simultaneously. And then you kind of weight the impact of one parameter on the model outcomes while taking into account the variation of the other parameters in the model. So usually in a simple way, one way deterministic analysis, one parameter you vary and see how it is impacting, one or two parameters you vary and see how the output is getting varied. One of the best way to depict it is by tornado chart. The output here is whatever you are getting from the models, whatever the outcome is. And if you vary certain parameters, how that outcome is varying, basically. So that is depicted in the tornado chart, and that's the best way to show it. On the other hand, uncertainty analysis, well, your model may have population. So what is the size of the population, for example? That's the you are interested in knowing. Parameter sensitivity analysis becomes a part of it, actually. But I think it is more on population and structure. I mean, why do you say one particular structure of the model is the correct one? Why don't you choose the other one? So you have to give a reasoning for it, and that's what constitutes the uncertainty analysis. Okay, so so this was very quick, actually. I just wanted to give you a brief. What are the components that forms the decision tree? Well, there is 4 components that basically forms it. As you are seeing on the right, this decision tree has a box here where you are taking a decision. For a decision is whether to use new intervention or not to use intervention. That's the decision node. But there are chance node where you are not sure about. There's a probability that you have a side effect. There's 1 minus of that probability that you don't have a side effect. So that's called as a chance node, where the probability starts to play an important role. Okay, and then there is a branches of the tree, which is connected by the lines. And then the triangles are one which is a terminal node that you want to. This is an outcome for this particular path of the tree. What is the outcome that you are getting? What is the monetary cost that you are getting in this outcome versus rest of the terminal node? So that's the basic structure of the decision tree. Important to note here is a decision node versus chance node. So this paper is a very beautifully written paper by Ellen et al. 2018, and we are also taking into account this studies in our current work. And this basically, the title is cost implication of UK NHS, National Health Services, I think, of using 2 point of care testing. And this is for influenza A and B. And the point of care testing is 2 of them are there, one with the nasal swabs and one is the throat swab, which already exists. So a throat swab already exists, but nasal swab was the new one they were trying to do, and they wanted to see how is it better to use a nasal swab in a point of care testing, or it is better to stick to the throat swabs in a point of care. But not only that, they also were comparing with a central lab. So central lab is a gold standard that we do for testing procedures. So they wanted to see this rapid test of nasal swab, comparing that with throat swab, point of care, and also with a central lab testing facility. So is the cost evaluation, can we do cost evaluation? That was the goal of it, and for the influenza of that. And they evaluated these different outcomes, cost associated. So just to give you, how is this decision tree look like for that? So if you see, one thing to note here is the patient comes here with a flu, and it is given testing, 3 different types of testing, PCR testing, which is a central lab testing, basically. And then this is a test, ELERA, influenza A and B test, which is a nasal swab versus throat swab. So there are 2, they are comparing these 3 decisions. Which one is better to use, and what are the costs associated with it? So, And so you have to build it based on for example, if you do the testing, one needs to be isolated or not isolated. And if it is isolated, whether the testing has resulted in correct results or incorrect results, because testing always comes with is incorrect results or inaccuracy. So those things are also listed. So each of these trees has branches and has whether the patient is isolated or not isolated, and whether the test was correct or not test correct. So these are the three arms to it, and the decision has to be made on this thing. So what is the data we use? Well, the data this study have used is like sensitivity and specificity of the different tests. They used published resources quite a lot. And so these are the data that they were using to parameterize this. And so the results is a very interesting result. So they said they calculated the cost of each of the three arms in three branches in this tree. And then they found that point of care nasal swab saves approximately 242,000 per 1,000 adults presenting with influenza-like illness. ILI stands for influenza-like illness. So that was the main result. But then they also did an additional result. They found is the main cause of it is the why is it happening that, and why is the nasal swab so low? Is because the availability of the results is different, is quite less in nasal swab as compared to throat swab and PCR testing, for example. Maybe not with too much of the throat swab, but with the PCR, the reduced time availability of the test was the main reason. But there are other drivers that is driving this model, for example, cost of isolation and testing accuracy in each case. Okay, so beautiful example that gives a clear picture of how is it useful and where we can use it. So now there is different types of decision tree are preferred in different situations. What is the goal? Basically, that decides on whether you want to use a decision tree or not. So, well, this table is, everyone is aware of this tables about diagnostic test results on this side and true diagnosis on the right on the top side. So false positive, false true positive, false negative, and true negative. But if you are interested, if you are doing it in a clinical practice, usually the diagnostic comes first, and then you kind of there is a testing sensitivity and whether the test is correct, results are correct or not. Then you talk about which is a disease status. And that is if the study is about a clinical practice, then they use a test-based approach where test comes first, and then you get to know about whether that is correct or not. But in randomized trials, sometimes you have a control group and non-control group. So you already know the disease status in one group. So here the disease state comes first, and the test diagnostic verdict comes later. So in randomized trial, this type of tree will be helpful, the one in the bottom, whereas in the clinical practice, this is the type of the test tree will be better, which is called test-based approach. So again, order is important here, and it depends on what is the application in which we are using the decision tree. Well, this study is also coming from the study, this tree is coming from the study, which is from Rautenberg 2020, and it is showing the whole idea was to know whether this was for the cancer, basically cancer, and it was using disease. It's for randomized trial and disease-based approach. It was using, by the way. So. So what I want to show, I will be telling you all the details in later on examples, but here the important thing I want to note here is few things. In that we are computing this expected value, and the expected value is generated for each component, for this component first, and then for this component first, And can you see my cursor, by the way? I'm not sure if everyone can see my cursor. So I'm using my cursor, and I hope everyone is able to see it. But basically,
we can see it.
yeah, okay. So basically, the idea is that what is an expected value of this arm? So before we calculate the expected value, let me say what is given here. So there's few things given in this thing. So there is a cancer prevalence, which is going here. And this is 1 minus of prevalence here. And this is, if the prevalence, you have sensitivity, which is here, and specificity, which is here in this part. And so these are the data that we need here. And so the study has taken a prevalence from literature, and also taking this sensitivity and specificity here. And note one thing is that this sum is equal to 1. You know, these are mutually exclusive event that I mentioned a few minutes ago. So this sum has to be equal to 1 here. So this is sensitivity is 0.829. So 1 minus of this. And same way here, specificity is 0.855, and this is 1 minus of this. So these are the probabilities in some sense. Prevalence is also a probabilities, and you can represent it like that. Per population, a number of cases per population. And then you can, the cost associated with doing a test. Now, when you say the cost, what is this cost? For example, 4974 is the cost, total cost in this path. And what is this cost? Well, cost is related to test itself, how much it costs, the test cost, assessment, the nurse time, or the whosoever is doing the, and whether the treatment is done early or late, and that has related. So these are all, because if it is done early, the person would be having a better life and maybe working more hours. And so you can actually quantify that cost of productivity. You can quantify the test cost. You can quantify the assessment by the nurse or technician. So all things can go into this calculation of 4974. And that's the cost associated with this path. And same way you can do, for example, 9108 is in the false negative case here. Basically, this is related to different costs that are going in this arms. And then in this case, since there is no cancer, you know, this is screening cost might be there, or assessment cost again will be there. So that cost is 96 here, and same way in true negative case. So this is the way you calculate the cost. This cost is coming from the literature, from the published work, or from the pharmaceutical reports or something like that. And these probabilities are also coming from the literature. And the goal is which arm, which is better, which arm is better. And let's see, the expected value of this arms is 4974 times this probability 829 plus this cost times, as we did it in the previous examples that I showed, 0.17, and it comes out to be 5681, which is only this much part. Only this much part. And then for this part, you can calculate in the same way. You know, I am seeing this window actually on my end. So then you can compute this this little branch here. Again, the cost expected average cost. Expected is average cost here, and average cost here, you know, is 560. And then you can compute the average cost in this part, which is taking into account 0.04 times 5681, which is this expected value. So expected value comes in this node here, 5681, and 24 comes here in this cost. This is an average cost. Suppose if I forget about this arm, then average cost is 24, and I put it as a terminal node as 24 cost. So the expected value for this cost will be 5681 times 0.04 and 24, which is coming from here, times 0.96 here, which gives you. So for doing the testing for cancer, roughly it will cost 4681 and an average amount of money. So very simple example, but see how the data is being used, how we calculate from right to left once the data on a cost and a probability are defined on a decision tree. So there are common, when we talk about using a diagnostic test to use a decision tree, there are common two mistakes that has been observed in the, and again, this is, I have not browsed the very good literature, but I'm using this, some of the studies that I have found it, which is one is this one. This is a recent study basically, by the way, 2020. So one of the thing is, many of the study that are using testing has main important thing. They don't talk about testing accuracy. And this is very, whether test negative, test positive, and false positive, false negative, all these things. The test accuracies are not incorporated. And that is very critical if you're talking about testing disease-related aspects. Now, different aspects that is also have not been seen in some of the studies is treating sequential diagnostic as independent. What that means is, suppose there is you are diagnosing for some things and then you are diagnosing again for something. They use it sometimes, some of these studies, in a two different tree. But the result might be related to one diagnostic test. So we need to, so second part, sequential diagnostic is independent. Instead of independent, they should be dependent. That is what I'm saying. The result of one test should depend on the result of, what you claim from a diagnostic test too. So we need to know whether diagnostic 2 will be performed, whether the results of diagnostic 1 are negative or positive. So this is the solution to that. First of all, to include the testing accuracy. And the second of all is to use that idea. If you know certain information, that is the result of diagnostic 1 you already know, for example, then you have to use it in the decision tree in a dependent way. Okay. This is an important aspect that this study is talking about. So some of the notes, so as I said before, the probabilities are listed here, but note one thing, this probability 829, which is the sensitivity, is a conditional probability. I talked about conditional probability, and that's the conditional probability that we are talking about here. And it's very, very important that we are not taking into account, because sometimes this conditional probability, if we do not take into account, we might get an error in that. Also, one thing, as I said it before, the sum is equal to 1. So 0.829 plus 0.171, these are mutually exclusive events, and their sum is equal to 1. The costs are shown in the endpoints. This is there, these are the cost. And folding back process, that means the way I was calculating, first you calculate the expected value on this right arm, and then coming from right to left in calculation of expected value. And that's what is called as folding back process. So now I've given enough components of the decision tree and its backgrounds and what type of maths is used. But now let's talk about the precise steps that we follow in stages in the development of the decision tree. So I think, okay, so there are 4 stages. One is you have to define a question. That's very, very important. Define what is your question, because I think the question is important for any studies. And this is very important to design the model structure and type of the decision tree to use. For example, if you are talking about randomized trials, that is one type of tree, whereas if you are talking about clinical situation, then it is a different type of tree. Okay. Model parameterization, then what type of evidence we have to collect, for example, to parameterize the model. And then basically putting everything together and calculating each arms, for example. And then exploring uncertainty. Sometimes we are not sure of some values, model parameters, and we are uncertain about. And I'll give you an example where we can go wrong. So this is a very simple examples, and in this, so I took it because health economics was new for me, and so I kind of, should I go to health economics graduate school or directly go for work in a real world after undergraduate degree? So this is a question in hand, whether I should do the graduate school in health economics or I should start working immediately. So that's the question. So how do you conceptualize it? So first of all, you have to know what are the factors that goes in this decision. in making that decision possible. So for example, the tuition of the graduate school might go, room and boarding might go, opportunity cost might go. So all these things can go into that and many more factors. But again, this is a simple model, so I'm just taking few factors into account that decides the decision tree. So again, the decision tree is whether you should go to the graduate school or you directly go to the work, real world work. So now the question is of parameterizing these things. So suppose a tuition, room, board, opportunity cost, all of these things are there. So you suppose graduate school take 2 years. So then you talk about you spend $55,000 for tuition, room and board cost this much, opportunity cost this much. But basically opportunity cost is you're not getting a salary during the time of the graduate study. So that's this much, for example, for 2 years. So total comes out to be 170. And then the anticipated 5-year salary after if you get the graduate degree, what is the benefit that you will have a higher salary to begin with, right? So that's what is 600,000. So net present value of going to the high school is the health economics graduate school is 600,000, which is the salary that you will get with the degree, graduate degree, minus the cost that you have spent in doing the graduate. So that comes out to be. But if you directly go to the real world, you will have a salary of something first 2 years that you are not getting in the graduate school. And then minus the expenses, some expenses that you might have during that time. So, and the final 5-year salary is, since you do not have a graduate school degree, therefore the salary will be less for you. So net present value in the no graduate school degree is around this much, which is the sum of 330 plus 80,000, 100 minus 20, comes out to be something like that. So, so this is the net value. So basically, this is the model parameter and finding the evidence. For example, we need where to find tuition, where to find the cost of room and board, where to find the opportunity cost of salary. We need to find these studies. I'm not talking about evidence right now. And then populate these models with evidence that we did here. And so the question is, which one is net present value is better? Well, it is very clear with going to the graduate school is better, and therefore go for a graduate degree. The decision is made. Now you can do explore uncertainty. And why do you need to do explore? Well, we missed many factors. For example, we filled how the future salary will increase, for examples, every year. We forget about cost of living. We forget about type of job. All these things can be quantified. And then we can think about uncertainty in what? So for example, opportunity cost of the salary, $100,000 is not static. There should be, it should range from 90 to 120, for example. So then you vary in that range and see what would be the model result will look like. So, so different reasoning will give you different type of uncertainty analysis. So this is a very beautiful example. I give you one more examples, and I think I'm running very late, but I will be very quick. So should we expand precision here? Suppose the question now to us is, I want to, so now note there in the previous examples, we did not have any chance here. The question was whether you should go or not go. So there is no chance involved in it. But now suppose you want to, another example I'm asking, should we expand PRECISIONheor and make it a bigger company or not? So, so then we have to think about what are the factors that goes in the economic evaluation of the question. So for example, what is the cost of expansion? How much it will cost to expand the PRECISIONheor? And whether the next year, what is the most likely knows that there's a chance involved now, whether the next year there will be a good or bad economy, for example. And you can actually, there are models to find out these chances, for example. So, so here now, this is the, this is a decision tree here, whether you should go and expand it. And the cost of expansion is $1.5 million. And don't expand it, the cost is just a 0. And if you expand it, then let's say from the literature, we get having a good economy is 40% chance. And then there will be a profit of 6 million if there is a good economy. And then there is, if it is a bad economy, there will be a profit of 2 million, let's say. And same thing here in this arm, for example. So, so then you can calculate again the net present value here, which will be 0.4 times 6 million and 0.6 times 2 million, and minus, because this is a profit and this is the cost on this thing, and minus 1.5, and that will give you $2.1 million net for expansion. And for not expanding, it is 0.4 times 3 million and 0.6 times 1 million, and that will give you $1.8 million. So now, again, the question, so, okay, so it seems like expanding is better for precision here, based on 40% chance of a good economy next year. But then you could also talk about, well, it could depend on where will you expand, whether it is New York or Los Angeles or somewhere else. Then the location of expansion might be interesting. And suppose location of expansion is important, then the cost is, we are uncertain about the cost of expansion, because then it could range from a city to city, or from, so 1.5 million will be a range here rather than a single $1.5 million. And then political situation might affect it. So political situation might impact the probability of good economy and bad economy, for examples. So these factors, then you may have the confidence interval in these probabilities. So then you can study these uncertainty or the ranges of the cost and the ranges of the net present values in expansion phase and non-expansion phase, using this uncertainty on this on these variables. Parameters. And these parameters are the cost of expansions and the probability of good and bad economy, by the way. So very simple example, but beautifully. Now here the chance is important. In the previous example, chance was not important. Now, if you, slowly and slowly, we are making the model a little more complex. So the first one, the chance was not there. Second one, the chance was there. Now we are talking about, suppose if we want to do, we have two interventions, and can we talk about incremental cost effectiveness of each of the interventions? Now, can we do cost effectiveness analysis through the decision tree? And the answer is yes. So by the way, QALY is quality of life plus length of life. The product of these quantity is computed at QALY. So if you do interventions, intervention means a benefit for the population. So the QALY will improve. The quality of life and the length of life should improve. At least one of the two should improve. Quality of life or length of life. And QALY combines these two metrics basically. So if you do an intervention, and that the QALY should improve. So the question here is, if I'm doing this certain interventions, so let's say there is intervention A and intervention B. So B is the existing intervention and A is the intervention that you are interested in implementing. And so the effects here is the QALY. The denominator here is the QALY here. And in ICR or cost effectiveness, we use QALY in the denominator. Okay, so what is the cost associated with implementing the intervention versus the ratio of the improved QALYness? So we make a decision tree here, and this is again is coming from the previous study that I just showed. The cost calculation here. So let me say, if you do interventions, then whether people accept that intervention or not, I mean, you can't just force the intervention. So there's an acceptance or not acceptance. And then if they accept it, there is only some people get the infection of some kind of disease that we are talking, and some other do not get the disease, for example. So what is the cost associated with it? Each branch, you write the cost. So there's a treatment cost, there's an intervention cost for if in the population of people who have accepted it, taking the intervention and still getting a disease. So that's this arm. And not getting a disease and acceptance is this one, for example. So if there are no interventions, then also you can calculate what is the possibility of transmission and non-transmission, for example. So there are column, this is the treatment cost in each of the paths or each of the branches, and intervention cost in each of the branches. So total cost is in first branch, for example, is 1500 plus 800. Okay, and same on same forth. And this is a probabilities that is coming from the literature, which is saying 95% of the chance that a people will accept the intervention that we have taken into account. So you can calculate the expected cost here. And the expected cost is basically this probability times the total cost. Total cost is $2,300, which is here, and 0.93 times the total cost, which is $800. And that will give you 905. So the average, which will come here, is an average of this arm among the people who accept the intervention. It's a average cost is $905, let's say. And same thing you can do in each of these subarms, and you can calculate expected value associated with it. Okay, so so this is the cost calculation. I've calculated. Now again, okay, sorry, and this I forgot. Now, so this is the process that we are going from right to left, and we can calculate the cost of this branch because we know the expected cost of this and this. So now 905.95 and 390 times 0.05 is give you 879. Basically, that's an average cost here in this node. Okay. So for doing the intervention, it cost $879. Okay, that's an average cost, by the way. And for not doing, you can also compute it in a similar way. It's $390. It's the same formulas. You can use it in this branch, and you can calculate that. Okay, so from the cost perspective, it is better to use intervention. But again, the cost is not sufficient because it depends on, remember in incremental cost effectiveness ratio, we have to find the denominator here, which is effects, which is a QALY. So you have to redo this chart. You have to redo this decision tree for QALYs also. So, so again, this is the QALY calculations. And each of the path, you have to get the data for QALYs from the literature. And then you can calculate the cost, expected QALYs. Expected QALYs for this, your probability times the QALY, and this probability times this QALY will give you 37.55. And then same thing here, 30.9. And then same thing here, which is 37 QALYs for this doing the interventions. And not doing the intervention, it is 30 QALYs for that one. So again, so then we can form a table here for cost that in the previous slide that we had, and QALYs in this, and then we can find the difference here, the ratio of that, and that will give us a value of here. And then we can study ICR using this two-dimensional chart, which is not the focus of this work. The focus is actually how do you compute it. So I'm almost end. There is also one more examples, and I think I have few minutes. So there's a difference. There is a difference in deaths between vaccinated and non-vaccinated individual of meningitis. So the deaths are more in vaccinated and non-vaccinated. Can you find it out? And so this is a very simple example. So you have to build a tree first, whether they vaccinate or do not vaccinate.
Anuj, you may want to go quick and just leave some time for questions just in case anyone has any.
Okay, so well, very quickly, I just want to show you the final, this verdict here in number of deaths in the vaccination. It's the same calculations. Finally, this last project that I want to talk about is the work that we are doing with Jason leading the group. Is a Abbott project, and this is about the point of care testing. And this in coming November, December, the COVID-19 will be also transmitting along with the influenza season during the influenza season. So the question is, they have a rapid test. Is it beneficial to use a point of care? What is the value of using a point of care testing? for influenza-like symptoms for US and European Union market. So we have used many features in it, like compliance to the decisions after the test results, capacity of the facility, sensitivity, and so we have also used a secondary infection. If you detect it wrong, the test, and the population and the person goes in the population, it spread the secondary infection. And again, there is a multiple disease here, flu and the COVID. So we are using a decision tree in that. So, well, I will stop here, and there are references, and I would be happy to share these slides with anyone who's interested. So thank you very much for listening to me. Jason. Hello.
Oh, sorry, I was on mute. Thank you very much, Anuj. Really appreciate you walking through the different decision tree approaches. Anyone else have any questions? We have about 5 minutes. Talk about decision trees or anything else.
Yeah, I mean, it's very simple, very basic, and I hope, and you might have done it at various projects.
Don't be shy. Don't be shy.
And I'm a very approachable person, so you can also send me an email later.
Hey Anuj, this is Priti.
Hello.
So that was a great presentation. Thank you very much. It was very interesting. I'm wondering, is there any time horizon concept applicable to the decision tree models? And if yes, then how to choose the time horizon?
Yeah, so it, again, depends on this is a very very good question you're asking. And usually the purpose if the time horizon is, you can incorporate different time points. But you see, if we have multiple time stages, then the tree will become very complex. So every time stage will be, but if you are talking about the starting stage and the final stage, then it will be interesting to work with a decision tree. But if you are interested in different timeline, then there are different models, the other models to use, and decision tree becomes very complex in that head. For each time step, you will be generating one. So yes, the answer to your question is, if you are only interested in time horizons and your current time, then it is just a 2 stages process, and you can incorporate a decision tree of first year, let's say, and then this final year, for example. So how is the first year is impacting the final year decision tree, and that's a continuous tree. And you can see the impact of initial years on the final years in that way. The only thing in that thing you have to worry about is how's the link between the two subparts are happening. For example, how is the probabilities of first years impacting the probabilities of the final year, for example. So I don't know if I've answered your question in that regard.
That was helpful, thanks.
Any last questions? Going once, going twice.
I do have a quick question for Anuj. So what happens when you have uncertainty on the probabilities themselves of transitioning?
Yes.
But you have a big idea of distribution of these probabilities themselves, but there might be competing distributions. So how do you do the sensitivity analysis there, for instance?
Right. Thank you, Oliver. Yeah, so I think you are one of the main experts, but I would, one of the way I have been doing, and you see, sensitivity and uncertainty analysis, according to me, is nothing new. I mean, we use the same methods in one method versus another. So I use it in dynamical models, which is called global sensitivity. You vary many of the parameters that you are uncertain at the same time in this distribution. And the question is then, what is the metric you use for? So sometimes they use Sobolev test. Sometimes they use partial rank correlation coefficients, for example, which takes into account the impact of one parameter while taking into account the variation in other parameters. Let me understand, your question is about how do you estimate the distribution, or your question is about how do you capture the sensitivity analysis?
Actually, I guess it's about the caption, the two competing possible distributions. This reminds me of the asset model pricing, where we have this binomial tree, and then with one half going up and down, and then at the limit you have Black-Scholes equation, which is Brownian motion. But let's say that this is asymmetric, and you have other distributions. So you may have still a Black-Scholes type of equation, but with a different diffusion. And
right.
then which one is better?
Right.
So then you decide whether to use. How do you do a sensitivity analysis of that?
So as with a modeling study, we also do validation for this thing. And the way to do is you have to have some data in order to know exact distribution of your initial parameters. And I think there is Bayesian analysis, for example, you start with a prior, and then the data basically clips the distribution in the right posterior distribution. Okay, so there has to be a data that needs for a Bayesian analysis, we can do it very easily in that. The prior is shaped, the initial prior distribution is shaped by the data. What would be the shape of the your uncertain parameter is in that case. So that is one way of doing it if you are unsure of the distribution of the initial parameters.
So their validation is important. Yeah.
Exactly. So the data is guiding the validation. If you don't have a data, then we can't say properly what would be the true distribution, basically.
Great. Well, in the interest of time, I think we're at time. Thank you, Anuj, for the presentation and for the questions, everybody. And these will be, once SharePoint is up, we'll post this online as well, so you can have the recording and the slides. So thank you very much, and have a great rest of your day, guys.